we'll start with an example of what is the ratio of the intensities of two sounds if sound 1 is 10 decibels larger than sound 2. Okay? Um, so, for example, let's say sound 1 uh, is 80 decibels and sound 2 equals 70 decibels. Okay? And we want to know what's the ratio of I1 to I2. So, to start, remember that decibels, let's draw it this way, or write it out this way anyway. So we would have that B1 or beta 1 is equal to 10 log 10 of I1 over I naught. And beta 2 is going to be 10 log base 10 of I2 over I naught. Right? And so we want to find the ratio of I1 to I2. And so what we can do is we can solve this equation or these equations, one for I1 and the other for I2, and see what shakes out, right? So in the first case, or the first step, would be log base 10 of our argument is equal to beta 1 over 10 and log base 10 of I2 over I naught is beta 2 over 10, right? And so then we need to undo the log, and so this is basically raising both sides to the power 10. So I1 over I naught is equal to 10 to the beta 1 over 10, and therefore I2 over I naught is 10 to the beta 2 over 10, right? And so now I can take this ratio and, well, if we formally write this out, okay? And so what we can do is write out I1 over I2, and the I naughts are going to drop out, so then I'm going to have 10 to the beta 1 over 10 divided by 10 to the beta 2 over 10. And this is the same thing as 10 to the beta 1 divided by 10 times 10 to the negative beta 2 over 10. Oop. And exponents of the same number add and subtract. So this is, tried to make that more 1-like, and then it turned into looking more 2-like. So this is 10 to the beta 1 divided by 10 minus beta 2 divided by 10, which is 10 to the beta 1 minus beta 2 divided by 10. And you'll notice that the difference in the decibel sound, it doesn't matter that this is 70 and 80. It could be 190. Beta 1 could be 100 and beta 2 could be 90. As long as their difference is 10, then this ratio is going to be the same, right? So, then we would finally get I1 divided by I2 is going to be 10 to the 10 divided by 10. And notice this is unitless, okay? Decibels is a unitless number. And I didn't really explicitly state that in the previous video, but your decibels is a unitless number because the arguments of logarithms have to be unitless. So intensity divided by intensity is unitless. And ratios of intensities, because they're unitless by the same logic, this is also unitless. Now, this is equal to 10 to the 1, okay? And so, this is 10. So, what we mean by this is that the intensity of sound 1 is 10 times as large as the intensity from sound 2. What that means is that sound 1 is 10 times louder than sound 2, okay? So, and a sound of 10 times louder corresponds to 10 decibels. Now, that might lead you to think that this is a linear relationship, but it's not. It is logarithmic, okay? So, just because this turns out to be that a difference of decibels in 10 means a factor of 10 difference in intensity, does not mean that a difference in 2 decibels means a difference or a ratio of twice the intensity. Okay, you can do those calculations for yourself, but this gives you the recipe for how to do them. Okay, so what that means, or what this means, is I1 is 10 times I2. Okay, that's what this result is telling us, right? So that is a example calculation on how to use this decibel equation, especially if it's been a while since you've used logarithms, right? You got to remember how to use your logarithms and why to use your logarithms. But I hope that example makes mathematical sense. And we now move to the issues of interference in sound waves. This is particularly important for sound engineers, okay? If you are a sound engineer for a live performance, or if you are a architectural designer for some sort of performing space, then this is also going to be crucial, okay? But the idea is that if I have two sound wave sources, let's call this source 1 and this source 2, then we can again think of the sound waves as these pressure waves coming out, and our dark blue lines represent our compressions and our white lines represent our rarefactions. And where these meet, or where the waves cross, I should say, is going to determine what the total resultant wave will be, right? So you will get constructive interference when the same part of the waves cross each other. Okay. So where two crests meet, you'll get constructive interference, or where two troughs meet, you'll get constructive interference. Uh, or you will really get constructive interference where the waves meet and they are both at the exact same point in their wave cycle. Okay, that's when you will get constructive interference. What this means is for sound, this is where your sound is amplified. Okay, so if I have two speakers in a room and I walk around the room, I will be able to hear differences around the room as far as the sound quality is concerned. And so when I find the point or points at which this constructive interference is occurring, then I will actually hear the sound the loudest. And in many cases, this is not universal, but in many cases, it would be the quote unquote most pleasant. But if a trough and a crest meet, then you get constructive interference. And here you get cancellation. Okay? When they destructively interfere exactly, then you get pure cancellation. Okay? But so this is where your sound is either the lowest or it disappears completely. And so if I look at this diagram, then we can see that let's take these 2 points right here. Okay, so let me actually label these different colors. Let's label this one red. Let's not use red. We're already using red. Let's use purple. I don't know how much different that looks, but we'll roll with it. And green. Okay, so this solid blue arc corresponds to a crest. Okay, this solid blue arc corresponds to a crest. And notice at the purple point, it crosses with the crest of the other speaker, right? So I guess I really should say that this arc is from this speaker, right? And this arc is from this speaker, okay? And where these two crests cross, I will get constructive interference. But notice that these two paths that each sound wave took to get to this point right here, it'll have gone a longer distance from the first speaker than it will the second speaker, okay? So we're going to label this R1, and we'll label this R2, okay? And delta R is the difference between these two path lengths. All right. So if I were to lay them on top of each other, whichever one would be longer, there would be some difference, and that's what we represent by delta R. So when our two crests cross each other, this is constructive interference. And what this means is that these two waves are still in phase with each other. They still have crests at the exact same point in space, even after one of the waves has traveled a further distance. But if that distance is exactly equal to one wavelength, or in truth, a integer multiple of a wavelength, then you will get constructive interference. Okay? On the other hand, where the crest from speaker 1 meets the trough of speaker 2, this is now R1, and this is now R2. And to deconstructively interfere, you have to be out of phase by exactly half a wavelength. So if this difference delta R is exactly half of a wavelength, then I will get a trough meeting a crest, and we get destructive interference. Okay? When the path length is intermediate between the two, then you just get interference. Okay? And so your waveform will add, but it'll be a little bit jumbled. Okay? It won't be exactly canceled out. It won't be exactly added together. Well, it will be added together, but it won't exactly be canceled out, and it won't exactly be double, as in the case of constructive interference. Okay? It'll be a mixture between the two. So if you're in a room and you're just hearing interference, then you can still hear the music. It's just not going to be as loud as in the constructive interference case, and it's not going to be as quiet as the destructive interference case. But if both of these speakers are connected to the same signal generator, like if you have two speakers in a room and you're listening to a song, for example, if the signal generator, whatever you're using to play the song, is equidistant to both speakers, in other words, the wires that you're using to pump the sound from the source to your speakers, if these two wires are the same length, then you're not going to have any delay due to the speed of light, insofar as the signal getting from the generator to the speakers. Now, in practice, this is very slight, but if you had really, really, really long cables, then you might notice a little bit with a very, very fine detector. But for most, concert settings, that's negligible. But the point is that if I have two speakers and let's say this is a concert and I have somebody standing right here, the sound wave from this speaker and the sound wave from this speaker at the instant, let's say T1, at time T1, when the, let's say an exact point in a song is played through the speakers, the part of that song is going to reach our person from this speaker sooner. We labeled this source 1, so we'll label this source 2. So source 2, let's do it this way. Let's label this time 0 let T0 be the time at which the exact point in the song is pumped through the speaker. And then the time it takes to get from the speaker to our person, we'll let that be delta T. So if delta T1 does not equal delta T2, okay, then you will actually get different parts of the song at different times. Now, in a small room, this is extremely slight. You really won't notice it. But in really, really large concert halls, this can actually play a giant role in how one experiences the concert because they will hear what's coming out of the speaker closest to them first, and then they'll hear a slight delay from the second speaker. Okay, so that is possible. But if that occurs and these two conditions are not met, then you simply get an interference between the two, and the overall experience can be a little bit muddled, right? So a lot of people, you want to stand, as you can see, right between the two speakers. You're going to get constructive interference. And the times from both of those speakers are going to be exactly the same. So one place to stand in a concert, like a rock concert, would be right in the middle between the two speakers, or you want to stand close enough to one of the speakers that it drowns out the sound from the other speaker and you don't really hear that delay, right? So, and this is also why a lot of venues tend to angle their speakers outward. Oh, that's terrible. As opposed to facing each other like this, some venues will slightly angle their speakers outward, so there's the people over here are going to hear this speaker much more easily than this speaker, and that delay effect doesn't really, it's not really a problem. Okay. All right. So we now move to the issue of standing waves and air columns, right? And this is going to mirror standing waves on strings very, very closely, right? But why do we care about standing waves and air columns? Well, just like with standing waves on a string, you hear a tone when the standing wave is on the string, right? That's when you really hear tones. When you play a musical instrument like a flute or something like that, where you have a closed end on one end of the instrument and an open end on the other end of the instrument, some similar things happen. But the bottom line is that to produce musical tones, then you need to put a standing wave pattern in your instrument, right? And so for the basics, and by the way, this is what we call resonance, okay? We talked a little bit about resonance with the waves on the string, but resonance in pipes occur when a wave is generated at one end. So like this would be your mouthpiece. This is the open end of the instrument. And your sound wave hits the end of the column, but when it hits this boundary, there's a pressure differential at that boundary. So some of the wave is transmitted into the air, and that's what we hear as the sound, but some of it is then reflected back to the source. And if the source is constantly producing this tone by, continually breathing into the instrument, then you get this reinforced standing wave pattern. Okay? So, you will get some reflection and transmission at this boundary. All right? Well, there has to be some transmission or you wouldn't hear it, right? But because of the pressure differential at the boundary, you will get some reflection. Now, why is there a pressure differential at the boundary? There's a pressure differential at the boundary because your node represents a point where your particles don't really have much displacement. And if you think about it, that should make some sense. Because the particles are up against the boundary, there's really nowhere for them to go. So they're not being pushed around with rarefactions and compressions. You're going to get your maximum compressions and rarefactions at your antinodes. And because you get your maximum compressions and rarefactions, these are by definition changes in pressure. And so, whatever the pressure is in the atmosphere, your pressure at the antinode will be different, and you will get a pressure differential, and you will therefore get reflection and transmission. Okay? So, when you have a single node and a single antinode, this is what we call the fundamental frequency of your pipe. Okay? And therefore, because I go from a node to an antinode, and then that gets reflected back, this is 1/2 of a wavelength. But it went twice the distance of the pipe, or 2L. So for your fundamental tone, 1/2 of your wavelength is equal to twice the length of your tube. And that leads us to this expression where if I solve for lambda 1 equals 4 times the length of my pipe. And if you think about it, that should make some sense. Because for a full wavelength, I go one length of the pipe. Oh, yeah. Never mind. Hang on. Let me draw this. Okay. So it's easier to draw these if we put in an equilibrium line here. So for one length of the pipe, I go from my node to my point of maximum amplitude, and then from my antinode, and this is length L, by the way. It took me length L to do that. And then it takes length L to go back down to the node. And then it takes length L to go to the next antinode. And then it takes another length L to go back to the next node. Now, this is exaggerated a little bit. I didn't do a really good job of keeping my sine wave consistent, but you get the idea, right? Each of these represents one length of the pipe. So to go from one full cycle is 4 times the length of the pipe. So our fundamental tone in a pipe open at one end and closed at the other is 4 times the length of the pipe. And remember that V is equal to lambda times F. And V is the speed of sound in air if we're dealing with woodwind or any wind instrument. Okay, so if I know the speed of sound in air, then I can calculate the frequency, right? So if lambda 1 equals 4L and V equals lambda F, then F1 has to equal V over lambda 1. But if lambda 1 equals 4L, then F1 equals V over 4L. Okay, so if you have a wind instrument, then you can actually calculate the fundamental frequency that that instrument will resonate at if you know the length of the instrument. So, in the cases of a pipe or a flute, then you'd be very, or it would be very easy to measure the length of your flute. Now, for a lot of wind instruments, some of your brass instruments like your trumpet that are really, really windy, right? It'd be much harder to actually um, measure the length of your pipe, but in principle, this still holds. Okay. So the next resonant frequency pattern that establishes a node at the closed end and an antinode at the open end is when we have 1/2 of a wavelength plus 1/4 of a wavelength, or 3/4 of our wavelength. Okay, so the length of our pipe is 3/4 of lambda, which we have right here. And if we solve that for lambda, then lambda is 4/3 the length of the pipe. And our frequency is therefore 3 times the speed of sound divided by 4 times the length of the pipe. And then the next resonant pattern where I have a node at one end. And again, you'll notice that we're increasing the number of nodes by 1. And therefore, we're also increasing the number of antinodes by 1, right? So here I have 1 antinode. Here I have 2 antinodes. Here I have 3 antinodes, and so forth. So all of our nodes and antinodes are just increasing by 1, right? And so you notice this pattern that for a given tone, the nth tone is going to be given by 4 times our pipe length divided by n. But you'll notice that none of these contain even numbers, right? None of these contain even numbers. So n is just equal to 1, 3, 5, 7, etc. Where 1 is, of course, your fundamental tone. N equals 3 correlates with lambda equals 2. N equals 5 correlates with lambda equals 3. And n equals 7 correlates with lambda 4. Okay. So, do be aware that for pipes closed at one end, your index of your overtone is going to increase not by 1, but by 2, and everything is odd. Okay? Another situation that can occur is what happens with pipes at open at two ends. Well, resonance occurs when I have pipes with 2 open ends, when I have antinodes at both ends. And that means that there has to be a node somewhere inside the pipe. So the fundamental tone here is when I have a node right in the middle and I have 2 antinodes at the ends, and this is half of a wavelength, right? Because it would take another, my standing pattern would look something like that, right? For the full wavelength. So this is half of a wavelength, and it is twice the length of the pipe, right? Because, well, the wavelength will be twice the length of the pipe. So in other words, L is equal to 1/2 lambda for the fundamental tone, and therefore lambda 1 is equal to twice L. Okay, so if I had a pipe twice as long and I were to establish this pattern in it, then that would be the condition when the wavelength equals the length of the pipe, right? Which is exactly what we see here. But before we go there, let's come back and remember that our frequency is equal to our speed divided by our wavelength. So that means that F1 is equal to V divided by lambda 1, and therefore this is equal to V divided by 2 times the length of the pipe, right? So my first overtone occurs when I still have antinodes at both ends, but now I increase the node inside by 1, and that means that my nodes have to occur here. And this is 1 full wavelength. So the wavelength for the first overtone, or for n equals 2, is just going to be the length of the pipe. And therefore the frequency is V times L. And notice that this is exactly twice as high as the fundamental frequency, which that should make some sense. If I double the wavelength, then I double the frequency, right? So the next overtone occurs when I have 3 nodes inside and I still have to have 2 antinodes. And so 1 full wavelength, 1/2 of a wavelength, and then 3, whoops. My wavelength ends right here. Okay, so there's my wavelength. And I have 1, 2, 3, 4 sections, but I have 6 possible half wavelengths, right? So let me kind of explain what I'm talking about here. When you draw your pattern in this form, I have a quarter of a wavelength here. 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 And then I have a quarter of a wavelength here. And finally, we have a quarter of a wavelength here, okay? And you can see because I have, 1, 2, 3, 4. This is 1 wavelength. Okay? So 4 of my segments make up a wavelength, but I still have 2 segments on top of that for the entire length of the pipe. So my length of the pipe is equal to 6/4 of my wavelength, or 3/2. And because L equals 3/2 of lambda, therefore lambda will equal, the second overtone, or lambda equals 3, will equal 2/3 the length of the pipe. And the frequency associated with that is 3 times the velocity divided by twice the length of the pipe. And so you'll notice that F2 is just 2 times F1, F3 equals 3 times F1, and so forth, right? So we've already gone over the waves on a string with very similar results, right? So as my harmonics change, um, and I move up in my overtones, my frequency associated with each successive overtone is just the number of that overtone times the fundamental frequency, right? So, hopefully that makes some sense. And in the next installment, we will look at beats and the Doppler effect.